Fossil fuel production, factories, they produce a lot of carbon dioxide. We all know about climate change, and this is undisputed now that this is a man-made issue. One of the potential bridging technologies for us to transition into renewable energies, but to reduce the carbon footprint of existing fossil fuel production, is actually what we call geologic carbon storage, which is effectively capturing carbon dioxide from these point sources and then injecting it underground to store it in the long term. Now, this has been trialled and is ongoing in a number of locations, and it's being investigated globally and is a really important technology, and effectively one of the only technologies that can help us reach our current carbon emission targets throughout the world. So it's a very important technology. One of the issues with geologic carbon storage is the long-term security of that carbon dioxide. And one of the ways we can actually enhance security is by turning that carbon dioxide into solid rock. Now, that's a natural process. Rocks like this, which are limestones, are effectively a product of this natural production of these carbonate rocks. But bacteria and microbes actually can enhance the rate at which those rocks form. So we're interested in looking at how microbes can enhance the formation of these carbonate rocks and therefore lock this carbon dioxide away in a stable and long-term form. We're all looking at the communities of bacteria that live underground and how these communities may enhance geothermal heating as well as the carbon dioxide storage.
We work in collaboration with the Big Pete National Coal Museum. Our work is focused on understanding the role microbes might have in not only carbon geosequestration, but also in groundwater heating. And because of that, we developed this technique to sample in situ and to process DNA and eventually to sequence and analyze it with a computer. All that in situ without the need for Wi-Fi, this is internet access, or external power sources. So everything we did was battery powered, and that's quite relevant for all fields, because until now there was a big hurdle in transporting samples from one site and then to the lab. And with this we may take the next step in our research where we can actually do science in the field.
So my part is to look at the geological aspect, which will then integrate with the microbiologists in Aberystwyth, which are developing the microbial techniques to help and enhance the storage. And this will also integrate with the engineers work in Cardiff University, where they are modeling how the whole system will work and assure stability for hundreds of years, if not thousands. The important part is to make sure that the CO2 stays in the subsurface. This is a typical seismic section from the East Irish Sea, and part of my work is to map the top of the reservoir intervals, which are these horizontal lines, but also importantly to map faults that intersect the reservoirs. So this is a continuous work where you map all these vertical structures that can constitute leakage pathways, and then you end up with these 3D maps of the shape of the faults. So we can get their orientation, but then when we apply stress parameters to see how they react under stress and under pressure of the ejection of the gas, we can see which ones will tend to move or stay still. And we can also use some other parameters to identify how much stress, how much pressure you need to make them reactivate.
In the NRN project, I'm working as a research fellow, and I'm looking into the numerical aspect of the problem. So if I illustrate you using this simulation, if you inject gas from some injection well, over the time, the gas will spread in the surrounding geology. Once the gas has been injected in the ground, our objective is to ensure that the gas is contained in underground environment. This is a very novel way of converting anthropogenic carbon dioxide from the greenhouse as an atmosphere to deep underground as a solid mineral, which will ultimately reduce the overall greenhouse impact globally.
collaborators at Cardiff University and the British Geological Survey have been looking at the potential of mine water from abandoned mines as a geothermal source for a while. However, the actual role of microbiology has not been considered. So we're particularly interested in this because there is a great potential, particularly in Wales, because there are so many abandoned mines. And it's not the same geothermal as, say, somewhere like Iceland, where this is like what we would consider to be deep geothermal energy. This is what we consider to be shallow geothermal energy. We're not talking about high temperatures, but even a few degrees of warming in these waters is enough for us to recover, to then generate energy for use by people and businesses and homes.